Okay, everyone. So your exam is coming up. Your final exam is coming up very soon. Um, there are going to be 55 questions. There are a total of five questions from that, which will be bonus. Um, what I'm going to do is I'm going to look at you know, I'm going to put every question in as 2 points apiece, and then I will adjust the score based on um, out of 100 points. So what that means is you can potentially earn a 110 on this exam. Now, the next thing to know about this is that our exam timeline. So our exam is scheduled for, and the university's got scheduled times. Our exam is Wednesday, December 11th, from that's 10 to 10:58 until 10:30 a.m. Um, that's when the exam's going to be open. If you have a schedule conflict with that, if you have something like you got to go to work or something like that, I need you to communicate with me directly. I can make an accommodation, but I need you to communicate with me. I can be flexible, but I need you to, talk to me before the exam. And I'm going to post this as an announcement as well. Um, but that's when the exam is going to be kind of baseline. That's when it's going to be. So that is, and what I'm looking at here, share my screen, share this window. Yeah, that's what I wanted. Um, this is the university's final exam schedule. Monday, Wednesday, Friday, 10 till 10:50, December 11th, from 8 until 10:30 in the morning. You're going to have the whole 2.5 hours to do that. Um, I'm going to be at my computer available in the event that something happens. But again, I need you to email me and saying, oh, well, I thought, our other exams were this way. I thought this. Well, I'm saying it now. I'm making it clear that this exam is different from our other exams. So I just need you to contact me. Um, and like I said, I'm flexible. I can help out. I can accommodate, but I need you to communicate with me. Missing the exam and saying, oh my gosh, I know this. Um, that's not really going to work very well. Okay, so with that all in place, what I'm going to do is just kind of start working through the semester. Um, if you have any questions, if you have a specific question related to, maybe one of your grades or anything like that, if it's about a grade, let's wait until the end of this meeting. If it's a general question, if it's a topical question, add it to the chat, unmute yourself, say it aloud. But we started the semester talking about physical properties. Physical and chemical properties. Are we going to get in to use a note card? Or are we going to? You can use one note card. So, condense everything down to a reflection of what's on that final exam review doc that I posted. It's an announcement on our Canvas site. Um, so yeah, everyone gets a note card. So I will make that so it's part of my announcement. Okay, now next up is we talked about physical and chemical properties. What are physical and chemical properties? Well, physical properties are things like the color of something is a physical property. The mass is a physical property. Density is a physical property. A chemical property is a measure of kind of how reactive, like basically you could say it as the chemical reactivity of a substance. Um, that would be a chemical property. And with that, like the smell of something is a chemical property because the smell is chances are what you're smelling would be like the a product that's generated by something. Like if you smell, you know, yeast when you're making bread or beer or something like that, well, that's because you're smelling compounds that substance is producing. So knowing what a physical and chemical property is, knowing what a um, physical or chemical change are as well, properties. Those are also important to know. Um, Now, I want to highlight this one in particular, density. I highlight this just because, well, it was, we did some calculations related to this. Now, units for density, or, basically what density is the mass of a substance relative to its volume. And the way that that's calculated is the mass over volume. Now, I always like to think about whenever it comes to mass and volume and density, I always like to think about a brick or a cinder block. Um, and let's go with a brick. Let's imagine that brick is, I know you guys have probably grown to appreciate my fantastic drawings this semester. And so let me look at that. It's just the site right there. So there's a brick. Let's imagine that this brick, we got two of them, two identical bricks, or space-wise, they're identical. And one of them is made of clay, and one of them is made of styrofoam. Well, the brick that's made out of clay, you can probably, make some presumptions about it. For one, it probably hurts if it falls on your head. And two, could probably break a glass window if you threw it at the glass window. But also it's like it's full. Like there's not any space in there. Um, you know, chances are you'd say, well, the mass of the clay brick is greater than the mass of the styrofoam brick. And you'd be right. The density of the clay brick is also going to be greater than the density of the styrofoam brick. So the reason is because both of them have the exact same volume. That means the length, width, and height of these are identical, but the masses are going to be different. So the density of the clay brick is greater than that of the styrofoam brick. So, let's say that the mass of the clay brick was 13.6 grams and the styrofoam brick was 2.5 grams. These are just random numbers. Let's say that their volumes were, let's say, 1.2 milliliters. 1.2 milliliters. You'd be uh, you'd be able to calculate this and say, all right, well, 13.6 divided by 1.2 is 11.33. So that's our density. Styrofoam, we've got 2.5 divided by 1.2, and we got a density of 2.08. Now, units for density, grams per milliliter. That's one way you can calculate density, and you can identify the more dense substance. Another way that you can calculate density is or a way that you can calculate the volume of a substance is by displacement. And so let's imagine that we've got these two bricks. We've got a solution, water. And we can measure the volume in this container. And let's say right here it's 150 milliliters. That's our baseline. Let me go ahead and redraw this line. So let's imagine that we've got this beaker with 150 milliliters of water, and then we drop a piece of gold in there. And the volume of this, after we drop that piece of gold in there, goes up to 160 milliliters. What's the volume of this gold? What's the amount or the volume change? So the volume went from 150 mils to 160 milliliters. Therefore, we've got the gold brick here, the gold block, has a volume of 10 milliliters. Now, can you use this to calculate density? Yeah. All that you got to do is take this piece of gold and put it on digital balance. Solve for it there. You get the mass divided by our volume, which is 10 milliliters. So you might see a question on your exam that says, mass of an object is this. It is placed into a beaker with a volume, or with water and an initial volume of 155 milliliters. After placing the piece of gold into that beaker, the volume increases to 168 milliliters. What is the density? So you look at the difference, the change, or the volume difference there. So physical properties, chemical properties, density, important things. Now we also talked about prefixes. And units. And this kind of brings in, actually, I'm going to say prefixes and numbers. When we talk about prefixes and numbers, well, your prefixes that are pretty common are kilo, milli, and micro. Okay, so if you take medication, chances are that that medication is you're taking milligrams of something. So you'll see this as mg. You might take a medication that's in micrograms, in which case it's using this mu. Thank you. Thank you. Micrograms, mu g, and then you might also say kilograms or kg. Now, what that relates to is kind of a base unit. And when it comes to mass, your base unit is grams. So G would kind of be your middle point, and you're either going up or you're going down from that. Now, a kilogram is 1,000 grams. This is the way that I learned this and that it is best for me to understand it. And it's easiest for me to understand it. 1 gram is 1,000 milligrams. 1 milligram is 1,000 micrograms. So let me rewrite that. 1 kilogram is 1,000 grams. 1 gram is equal to 1,000 milligrams. 1 milligram is equal to 1,000 micrograms. Okay, so those are kind of your baselines, or those are all the connections between these two. One other way that people will represent this is they'll say, well, 1 microgram is equal to 0.001 milligrams. 1 milligram is equal to 0.001 grams. And then 1 gram is equal to 1 kilogram. Or, sorry, not kilogram. Is equal to 0.001 kilograms. Now you're moving the decimal place quite a bit there. And when you do that, Another way to interpret this is to say 1 microgram is, and you can draw a connection between micrograms and kilograms with these prefixes. 1 microgram is equal to, put this in kilograms. I got one, let's see. We're moving our decimal place a bunch. So we're going to have 1, 2, 3, 4, 5. Second, I've got to make sure that I'm doing this properly. So that's going to be, we're dividing these by 1,000 each time. So that means that it gets us to grams. And then one more time. So we're going to have a total of 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 1 microgram is equal to 0.000000001 kilograms. Now, that is true. And you can also write this using scientific notation. Scientific notation is where we count basically the number of places that we move our decimal. I'm going to switch colors here. So whenever I write a number in scientific notation, what I need to be sure to do is have one non-zero digit followed by a decimal, and then any other values. And then you use, and times 10 to the, well, whatever exponent. So here what we do, we're taking this number, 0.000000001 kilograms, and we want to write this in scientific notation. The way that we do that is we count up the number of places, the number of times we move our decimal from where it starts. The way that I've written this number right here, this, I'm going to highlight, I'm going to draw a line over this. No, I'm not going to draw that. This number right here is written in extended or full notation. How many times do I have to move my decimal? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I've moved my decimal 9 places. Why did I move it 9? Why not 8? Why not 7? Well, because I have to have a non-zero digit. 1 is my first and only non-zero digit. So I'm going to write this number as 1. And in this case, I'm going to write 0.0 times 10 to the negative 9th. And I know that it's negative because, well, 1, I went from a very large unit to a very small unit. And another way that I know it is whenever I'm translating from full to scientific notation, my decimal goes right. So my decimal moves to the right. Now, if I want to take a number from scientific notation to full, what I'm going to do is I'm going to say, let's say I've got a number 1.46 times 10 to the positive fifth. Okay. Now I'm going from scientific to full. I have a positive exponent. So that means I'm going to move my decimal to the right because I'm going scientific to full, not full to scientific. Okay. When I go from full to scientific, then I use a negative exponent. Here I'm using, even though I'm moving to the right, here I'm moving to the right and I'm using, yeah. So I'm going to go 1 and move that. 4, if I put it here, that'd be 1. 6, that'd be my 2. 3, 4, 5. Now, done. And I'm just going to bring in this other marking to indicate the movements. 1, 2, 3, 4, 5. Okay, there we are. And so 1.46 times 10 to the fifth is 146,000. Now that's going to get us some of the important parts from Module 1. Let me look at my study guide. And if anyone has any questions, please don't hesitate to ask. Okay. Next up, we've got temperature. Units that we use for temperature, Kelvin. So when we talk about a conversion from Kelvin, well, if your temperature is 32 degrees Celsius and you want it in blank Kelvin, well, what you're going to do is you're going to add 273.3.15. So that's going to give us 305.15 Kelvin. Okay, so that's one of the items on there. Then convert from milliliters to liters. Well, that's very similar to what we did here. One liter is equal to 1,000 milliliters. As a result, if you have something that is 596 milliliters, well, that's going to be the same as 0.596 liters. Okay, so we've done density. Okay, subatomic particles. Let's jump onto that. Subatomic particles, we got protons, neutrons, electrons. Protons are positive, neutrons have no charge whatsoever, and electrons are negative. Now, two of these things, protons and neutrons, make up the nucleus of an atom. And so your protons give your atom a charge. If you have something that looks like this, plus, 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 this is 3 protons, N, that's a nucleus. Or sorry, that's the neutrons that make that are added to the nucleus. So we've got a total of 7 subatomic particles making up our nucleus. Of those 7 subatomic particles making up that nucleus, what is the overall charge of this? It's plus 3. Now imagine that this is an atom, and to that atom we add 1 electron. Now what's the overall charge of this thing? Well, it's plus 2, because 1 electron cancels out 1 proton. Now, if I were to add another electron, another, and another, what's the charge on this thing right here? We've got 3 positives, and then 1, 2, 3, 4, 5 electrons. So those 5 electrons cancel out 3, or 3 of those electrons cancel out 3 of those protons. So we're looking at something with a -2 charge. Then let's see, we got subatomic particles and charges, periodic symbol. And typically when you look at a periodic symbol on a periodic table or a symbol on the periodic table, you'll see something like this. Let's say 6, and actually, no, I know this one. So we'll say 3. and then Li and 6.94. Okay, so this Li is the symbol for the element lithium. The 6.994 is the average atomic mass. And then 3 is the atomic number. And that atomic number is the number of protons. So if I gave you something like this, and I asked you the question, how many protons does this element have? You'd say, it's 3. Done. The average atomic mass, also sometimes represented as the mass number, that is going to be protons plus neutrons. In the event that you're confronted with something like 6.94, you wouldn't say that it's, oh, well, it's 3 protons plus 3.94 neutrons. Instead, what you'd say is, well, this is going to be 3 protons plus 4 neutrons. Okay. So, next up, let's see. Okay, next up, we, in the next block of content, talked a little bit about what does a Lewis dot symbol look like. And a Lewis dot symbol looks at the valence electrons. In a Lewis dot symbol, what you're going to see is the single letter symbol for something, and then you're going to say 1, 2, 3, 4. How many valence electrons does an atom of this element have? Carbon here has 4 valence electrons. And so you see around that capital C in the middle, you see 4 electrons indicated. So in the event that you were to see something like this, and actually, let me rephrase this. Does carbon have a total of 4 electrons? No, it doesn't. Its valence electrons are the outermost electrons. Now, from the periodic table, you can figure out the number of valence electrons of numerous elements. For instance, 1, 2, then 3, 4, 5, 6, 7, 8. If we had something like, let's say, Ne, neon, right here. Neon has a total of 8 valence electrons. The reason that I know that is because of where it is on the periodic table. It is in this 8th column. Now, something in this column. Well, how many valence electrons is that going to have? 6. What about here? 3. Here, 7. Now, with that in mind, right here on the periodic table is fluorine. Fluorine has 7 valence electrons. Fluorine is also a diatomic element. So what that means is that fluorine loves to pair up with another fluorine to make F2. Now, here is what fluorine looks like. And here is what F2 looks like. Actually, I'm going to go, sorry, where I was drawing fluorine, just get another color and go with blue. Fluorine looks like this. Okay, so there's each fluorine atom brings an electron. And they kind of pool their, you could say their one extra or their unpaired electron. They pool them together. And when they pool them together, they come up with something where it's like, oh, well, we can share these. And when they share them, it's effectively like, well, this fluorine on the left, right, that's on the right, sorry. This fluorine on the left It's got 8 electrons. And you know what? Can't find my, okay, there we go. This fluorine on the right has 8 electrons. They both have 8 electrons, which is kind of the goal. They have a complete octet because that brings up the octet rule. Almost every single atom on the periodic table wants to get 8 electrons around them. Now, another way that fluorine can achieve an octet is by picking up an electron from somewhere else, from somewhere that doesn't want it. So what that looks like, if I were to ask a question for the Lewis structure, I just want to make sure that I'm actually I can go into this. That's not a question that I'm going to ask. But this right here is the Lewis structure for fluorine. This right here is the Lewis structure for fluorine gas or F2. So if I asked you for an element or the Lewis structure of the element fluorine, that's what this is. If I asked you for the Lewis structure for the molecule of fluorine, that's what this is. Now, oh, okay. Okay, so this would be an example of a single bond. Um, Another atom that's a diatomic element is N2, or nitrogen gas. And N2, in this lower right-hand corner where I'm drawing now, what that looks like is this, N2. Each nitrogen is going to bring a grand total of 5 valence electrons. And of those 5 valence electrons, here's what nitrogen looks like as an individual atom. There's 5 valence electrons. And here are another 5 valence electrons. When we kind of pair these things up, N2, each one of them wants to have, well, 8 electrons around them. How do they do that? Well, we know that there's going to be at least a bond to connect the two of them. So this right here, sorry, whenever we're drawing something, we can only draw the number of electrons that we have. And so we're limited to 10 electrons. How are we going to make that work? Because right now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we've got 10 electrons drawn. The single bond here represents 2 electrons. Now, if I were to do this, in this case, each atom has 8 electrons around it. But we can't do that because then we're just kind of making up electrons. If we did this, we drew a second bond, then we'd have to get rid of some of the electrons around here. Okay, so now what I've got is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's 10 electrons drawn, but do each one of them, or do they all have like a complete octet? No, they actually kind of exceed the octet. They have more than the electrons. So what we can do is we can do a triple bond. So this, I'm just going to label it as a 3x bond. How many electrons does that 3x bond represent? 6 electrons. So that triple bond represents 6 electrons. And so that's kind of the conclusion of our calculation there. A double bond represents 4 electrons. So you need to be able to identify how many valence electrons something has, how many electrons are around an atom. You need to be able to identify a molecule's Lewis structure, an atom's Lewis structure, and that's a lot of the stuff with respect to exam 2. Exam 3, oh, are you going to talk about elements that exceed the octet? Nope. Um, I'm not going to have any questions about those that exceed the octet. I think that a fair true false question could be, are there elements that can exceed or exceed the octet or have less than 8 electrons around them? So, and the answer to that is yes. There are elements that can exceed the octet by having, 10 electrons around them, or there's some like uh, boron that have less than 8 electrons around them. Okay, so, and thank you for the question. Any questions that you may have, just let me know. Actually, before I move on to exam three stuff, what I wanted to talk about was polarity. So polarity, I always kind of think about like a game of tug of war. Tug of war. In a game of tug of war, you got different strengths. And when we talk about polarity and non-polar, we're talking about strength of, well, kind of the pull for electrons. How much does one atom want electrons compared to the other? And if we talk about this, the pull for electrons, what we're really referencing is a phenomenon. Okay, sorry about that. I'm recording. Um, so I'll post it later. We have a phenomenon known as electronegativity. Electronegativity is basically a measure of how much does one atom want electrons compared to another. Um, Not every atom wants electrons to the same degree. There are um, elements that are more electronegative than others. For example, the most electronegative element is fluorine. Now, um, so fluorine wants electrons more than anything else. And as a result, whenever fluorine pairs up with most things, it is going to form a polar bond. I always kind of think about it like fluorine is like Hulk Hogan. No, not Hulk Hogan. I'll go with the Incredible Hulk. Fluorine is your Incredible Hulk, and most other atoms, well, they don't have the same strength. So let's go with something like boron and fluorine. Boron and fluorine has an electronegativity of 4.0, and boron's is like, I think it's like 2.3. Um, so fluorine is like pulling those electrons so much more than boron is. So that's ultimately what we're looking at with those. Um, um, so that's bond polarity right there. Now let's go on to exam number three stuff. With exam three, we talked about, or the exam three content, we talked about the kind of let's see, what's the word that I'm looking for? States of matter. And I think that everyone feels comfortable saying like the states of matter because it's kind of something like when you take a science class in like junior high or before, you know, elementary school even, that's what you talk about. Solids, liquids, and gases. And then there's always someone who's like, oh, but what about plasma? And yeah, you're not wrong. But we're talking about solids, liquids, and gases, SLG. Now, when it comes to solids, liquids, and gases, there are a couple of different charts that are worth knowing about solids, liquids, and gases. One of them looks like this, and today I'm out of drawing sync, so that wasn't particularly good. So we've got that line that gradually increases. Then we've got this one that's flat. Then we've got this one that gradually increases. Then this one that's flat. And this one that gradually increases kind of into eternity. Now, when we look at these, the parts that are increasing are the regions of these lines that are increasing. We've got let's see, I'm going to go ahead and label it as this is a solid. Then this is a liquid, and then this is a gas. So these regions right here, these flat lines, those flat lines are important because they tell you about, well, is so the y-axis of this graph is temperature, and then X-axis is heat added. Going from a liquid to a gas is going to be vaporization. And then going from a gas to a liquid is going to be condensation. So vaporization is this way, condensation is this way. Going from a solid to a liquid is melting. And then going from a liquid to a solid is going to be freezing. That way. So this is one graph that's important to know about different states of matter. Another graph, that wasn't a good straight line. Another graph looks like this. And what we have, this is kind of called, or it's sometimes called a triple dot diagram, or a phase change diagram. And this has some kind of wonky areas. So I'm going to go here and then that. Yeah, I'll just go with this. So this is going to have again, solid, liquids, and gas. And the axes of these, or of this sort of graph, are a little bit different. The pressure is going to be on the y-axis, and temperature is going to be on the x-axis. Now I'm going to change color just so I can throw some more text on here. In this first cell right here, this is going to be a solid. So what you can use this for is to look at temperature and pressure and determine coordinates and say, oh, okay, well, based on, a temperature of this and a pressure of this, this is where you'd be. So if your temperature was 100 degrees and the pressure was, 0.3, then you're right here. So under those conditions, whatever that material is a solid. Okay. So then what we also have is liquid up here and a gas down here. If the temperature were to increase, but the pressure remained the same, what would happen to this substance? Well, the temperature increases, we are going as straight a line as possible. And I'm doing my best to draw that as a straight line there. I'm intending for it to be a straight line. And we increased our temperature to right here. Let's say that our temperature is now 135 degrees. We're right here. Okay, so when our temperature jumps up like that, we went from a solid to a liquid. There are also changes where you could go from a solid to directly to a gas. And how would you do that? Well, let's say our pressure is 0.1. If we were to drop the pressure right here, and actually I'll go to 0.05. I'm dropping my pressure all the way to right there, but my temperature remains the same. I'm going from a solid to a gas. Now, that's the thing that I think lots of people like to remember that one, just because that is that process going from a solid to a gas is something that you've seen either like at a haunted house or at a football game or something. Dry ice. Dry ice goes from a solid to a gas. In addition to that, people like to remember this one because when we go from a solid directly to a gas, it is sublimation. And people like to remember the band Sublime. Sublimation. Okay. So those diagrams, need to know those. Need to know, like, in the event of this change, what happens? What about this change? What happens? Um, and then it's also important to know about the properties of solids, liquids, and gases. Think about them. There are a couple of diagrams in the PowerPoints that we had that looked at what does a solid look like at the molecular level? What does a liquid and what does a gas look like at the molecular level? And I always like to ask the question, what happens if this, sorry, what is the difference? Okay. The, okay, so sorry. What is the difference in the space between the molecules or atoms that make up a liquid, a solid, or a gas? The space is going to be the greatest in a gas. The molecules that make up that gas are over here and down here. A liquid, they're like closer in proximity, a solid, they're stuck. Because think about a solid. Well, a solid has a fixed volume, it has a fixed shape. Everything about a solid is like it's not going to move unless you do something pretty dramatic to it. A liquid by comparison, well, it sloshes around. A gas, if I for instance, if I were to belch right now, well, that gas that I exhaled is going to fill the room. And that's just going to be kind of gross and unfortunate. So think about those things on a molecular level. Then that was all a lead into talk about intermolecular forces. There are intermolecular forces and there's intra versus intramolecular forces. Intermolecular forces are kind of like the interstate highway system. I always have to do that in order to think about inter versus intra. Um, my like the interstate highway system takes you from Texas to Oklahoma to Kansas to Iowa or to Missouri to Iowa to Minnesota. Intra intrastate, well, that would be um, everything, all of the roads within a single state. So an intermolecular force or an intermolecular interaction is how two different molecules interact with one another. Intramolecular, well, that's all about looking at that individual molecule. So intermolecular forces, we've got a couple of different ones. There are dispersion forces. There are hydrogen bonds. There are Those are your two big ones. And then there's ionic interactions. um, Hydrogen bonds. Well, what you've got to have for a hydrogen bond is a hydrogen. And then you've got to have something like an oxygen or nitrogen or a fluorine. Okay. So that's what you're looking for when you're talking about an intermolecular force. Intermolecular forces are weaker than intramolecular forces. Think about that as the intramolecular forces hold a molecule together, whereas intermolecular forces are how two molecules interact with one another. Um, so that's important to keep in mind. Let's see. Um, Then one thing that I want you to be able to do, this is kind of going to be my last thing, then I'll just open the floor for any questions that you guys have. I'm not going to, there's still exam four stuff, but there's less exam four stuff. Um, for exam three stuff, we talked a lot about gases, and I want to make sure that everyone knows how to do a calculation with the ideal gas equation. PV equals nRT. I will give you that equation. What are the very important things to know about this is that your pressure needs to be in atmospheres. Your volume needs to be in liters. N is the number of moles. T is going to be in temperature in Kelvin. And R is a constant value that is provided to you. The toughest part about this is reading the question and figuring out what am I being asked for. As soon as you do that, like if the question asks for the temperature, well, then just think about this as I've got to rearrange this equation to get temperature by itself. How do I do that? And the way that, or sorry, how do I do that is your question. The answer to that question is, well, everything on this side is being multiplied to equal everything that's being multiplied on this side. So if you want to do the opposite, and that's what we're looking to do, we want to do the opposite of multiplication. So in order to do that, if we want to get temperature by itself, we divide the right-hand side of the equation by nR. And when we do that, we can cancel n and r on the right-hand side of the equation. And then we have to do If we do one thing to one side of the equation, we have to do it the same thing to the other side of the equation. So now I'm going to say divided by n and r. So I've got a new equation that is PV over n and r, and that is equal to t. And whenever I've got that, I'm ready to solve my equation. I would say that after you get this, one of the things that you're going to have to navigate is playing around with and making sure that you're like the way that you set it up in your calculator is fine. Um, you're going to do, or what I always do is I just put everything in parentheses. And another thing that I'll do from time to time is I'll say, what's pressure times volume? If this is 12 times 13, I'm going to go ahead and plug in 12 times 13, solve for that. That would be about 156. And then I'm going to divide by n and r. Okay. And I'm dividing by the product of n and r. So then I'm going to plug in what is n? N is 3. What is r? That's a constant. That's a value that you'll be provided with. And that's going to be 0.0821. So 3 times that is going to be 0.2463. And so then I'll erase all this. I think that's 0.2463. 2463. And there we go. So I will, when it comes to lots of math steps and a problem with multiple steps of math, I'm going to be super deliberate. I'm going to solve, enter, or plug, write it out. And then the next part, I'm going to solve, write it out. And one question that always surfaces regarding this is like, I'm not going to round. And so if my calculator tells me the answer is 0.2465444444444, I'm going to write every single one of those fours. I'm going to write all those, and then I'm going to divide by the number with the exact same kind of display. And once I've completed that calculation, only then will I do my rounding. So if I were to take this, for example, and I said 156 divided by 0.2463, I'm going to get an answer that is 633.373934 equals temperature. So I'm going to say, well, temperature equals 633.4. And that would be Kelvin. Okay. Well, I am going to open a new page and I'm opening the floor. If anyone has any questions, go for it. You can add it to the chat or you can say it aloud. I believe, yes, my computer is not muted, so I will be able to hear or planning to hear. But yeah, anything you got. And if there aren't any questions, I'm going to go ahead and um, say I hope you do well on the final. And I will send that out. Okay. Okay, cool. I got some questions. My first question, and go ahead and add them to the chat. They'll populate at the bottom, and I'll scroll through them one by one. My first question, can you go over bond angles, domains, and their shapes? 100%. Okay. First, take a drink of my coffee. So, oh, and after I answer these questions, I'll talk about the grading and how your final exam has the chance to replace everything. Okay, or every exam. Okay, so bond angles. All right, so when we talk about bond angles, what we're looking at, and the question, the area that you should be thinking about with respect to bond angles is we're looking at what are known as electron or E, I'll just say E, domains. Now, when it comes to an electron domain, that could be any number of a couple of things. It could be a shared pair of electrons, or it could be an unshared pair of electrons. Now, a shared pair of electrons, a shared pair of electrons is going to look something like this. I'm going to go ahead and just use X. X is my element. It's not a real thing. A shared pair of electrons would be, well, X and Y. Okay, so this right here is my shared pair of electrons. So that's two electrons. They are shared between atom X and atom Y. Okay. An unshared pair of electrons would be something like this. Element Z and there. And so I'm going to say Z, Y, Y, Y. Okay. So that, so actually, let me go ahead and do this. X, Y, Y, Y. Okay. So when it comes to electron domains, what you need to do is count up how many things are around that central atom. So in the case of this compound, ZY3, there are four things surrounding that. And of those four things, one is a USP, an unshared pair, and then three are, well, shared pairs. Okay. Now, in the case of XY4, well, in this case, we've got a total of four shared pair of electrons. Okay, so the difference being, well, how many shared pair, how many unshared pairs? In a shared pair, well, we've got four shared pairs with this XY4, and then three shared pairs with the ZY3. Okay, now when it comes to, well, so that's your domains. Now, the range that I wanted you guys to be familiar with was, let me look back at my review doc. Um, okay, two or three electron domains. Now, what I've got is I'm going to do two different compounds. I'm going to do, let's see. Yeah. Okay. Actually, here, there's a couple of different directions that I could go in. Something with, okay. Oh, no, sorry, just a second. I'm trying to think of a good option. Good. Okay. Yeah, there's one with, that's a good one for three. Uh, okay. Yeah, that's great. Okay. So for two E domains, we've got a molecule like carbon dioxide. Carbon dioxide looks a little bit like this. Carbon dioxide right there. These oxygen atoms are 180 degrees away from one another. These oxygen atoms are 180 degrees. And I'm thinking about 180 degrees. When I think about something and angles, I'm thinking about something have a like our total angle would be 360 degrees. Um, so thinking about this would be a 90-degree angle, not drawn well, but X and Y, X and X here are 180 degrees away from one another. So this is an example of a molecule that is considered linear because those two atoms, those oxygen atoms, are as far from one another as they can possibly be. And effectively, they're a straight line. Okay, now three E domains. What does that look like? Okay, so there's a couple of different permutations. That could be three shared pairs, could also be two shared pairs and one unshared pair. Now let's look at are unshared pair, or sorry, are three shared pairs. The molecule BF3. Now, this is an example of an atom, or boron is an example of an atom that can have less or can get away with having less than 8 electrons around it. And it looks like this. Now, what we are looking at is we're looking at this with respect to that central atom. That central atom, that boron, has three shared pairs of electrons surrounding it. These three things, they are as far from one another as possible. And so they are exactly 120 degrees away from one. And this molecule, since they are 120 degrees away from one another, this is also considered a, well, it's like a completely flat plane. And what this is referred to as is a um, trigonal planar molecule. The name for that shape is trigonal or trigonal planar. Now, for our other molecule, this is the case with our other kind of combination, is a molecule, draw a little divider here, with, say, two shared pairs of electrons and one unshared pair of electrons. We have NO2 minus. And what's that going to look like? Okay, so what that looks like is this. We're keeping in mind that we're looking at this with respect to our central atom. Our central atom here is nitrogen. Now, nitrogen there is going to have, and this whole molecule right here is going to have a -1 charge. The unshared pair of electrons, what they do is they occupy the most space. And so you can't really look at this and say, oh, it's just the exact same as our BF3. Instead, what's going to happen is that this lone pair of electrons, or this, yeah, right here, this unshared pair of electrons on that nitrogen, what that's going to do is that's going to kind of shift the angles a little bit. It's not going to be 120 degrees. Instead, the distance between here and here, let me change colors so I can highlight that a little bit more. Between here and here is less than 120. And this is considered, but this is, the shape for this is bent. So next, I got a question that was asked. I'm not sure what unit this is from, but how does it work when an element is stable with a charge like Na plus is considered stable, or like a noble gas configuration? Great question. So think about this as Na. Okay, we'll use sodium in group 1. So in group 1, a sodium atom has one valence electron. Boop. And that's its outermost electron. So that outermost electron is just out there by itself. And that kind of out there all by itself valence electron, it doesn't really have a lot to jump onto. And so what's going to very easily happen is that this electron is going to be lost. And then what happens is, I'm going to look at the periodic table real quick. So that sodium is going, sorry, a sodium atom. Let me erase this. Na has 11 electrons. What Sodium likes to do, and what it will easily do, is lose this one electron. And when it loses that one electron, now sodium has 10 electrons. If we look on the periodic table to see another element with exactly 10 electrons, what we see is neon. If we look at the noble gas, or sorry, the electron configuration of neon, it looks a little bit like this. Okay. This right here is happy. Every single electron that neon has is paired up. When sodium loses that one outermost electron, effectively, its new outermost electrons are all paired up because it's gone from 11 electrons down to 10 electrons. So it has a I'm going to put a negative there to indicate that it is negatively charged, but it's reached its octet. So if you think about it in terms of, well, how can an atom be happy? Well, it can be happy by reaching the same number of valence electrons as a noble gas. So I have a follow-up. So it loses one and it gets positive. I'm sorry. Yeah, sorry about that. I screwed up. Yeah, it should be a positive because it lost one. And yes, that's absolutely right. Um, Now I have one more question, and that is, can you calculate pH based on hydrogen ion concentration? Absolutely. So when you see something like this, H plus hydrogen ion concentration equals, let's say that it's 0.1 molar. Well, the way that we figure out a pH is equal to the negative log of the hydrogen ion concentration. So negative log of 0.1 is, I believe that is 1. Um, Basically, yeah, that's 1. So how many places did you have to move the decimal? You had to move it one time. So that's a pH of 1. If you had hydrogen ion concentration of 0.0001, well, then you'd move the decimal 1, 2, 3, 4. So our pH here is 4. So then a fair question is comparing solutions. Solution A has a hydrogen ion concentration of 0.01. And then B is H plus 0.001. Which one of these is more acidic? Well, you could do the calculation and you figure out that this has a pH of 2, this has a pH of 3. Alternatively, you could say, well, the higher the hydrogen ion concentration, the more acidic a solution is. So you'd arrive at, well, this, but again, you could also use the pH and see that it is 2, so that's higher. All right, that's lower. The lower the pH, the more acidic. Okay, I think, are there any other questions? Sorry, this is a few lectures. Yes, I will, yes, sorry, I will take care of that before, let's say before the end of next week, I will get that situated. Um, okay. So now what I want to do is just talk about exam grading. So exam 1, 2, exam 4, and final. So if you look at your grade book, right now there's a bunch of stuff in there. And there's still some stuff that I need to add. We spoke about, let's say, um, okay. So I got it. Um, just a second. Um, the is it okay if if we only focus on study guide you posted on Canvas? What are your questions? Because that's what I started with. That's where I've kind of been, that's what I've been spending the day doing. That's yeah, that's how I've been going through this review. Do you have a question for Rana? So this was where I was going to wrap things up because I started this at 10:30. Okay, thanks, Amira. Um, so I'm just going to do exams and talk about the exam scorings. So let's say that you got a 92 on exam one, and then let's say you got an 80 on exam two, a 75 on exam three, and then let's say you got an 88 on exam four. If you take the final exam and you get a 92, effectively this 92 will be compared to each one of these scores. And provided that the final exam is higher, any grade that is lower than the final exam will be dropped. I've had this going throughout the course of the semester. So like exam three, or sorry, exam two, if you got an 81 on that, that was also brought into, or sorry, that was also compared to exam number one. But the 92 being higher than both of those, well, or sorry, the score on the final being higher than both of those, that one will be dropped. So your final exam is a great opportunity to bring up basically every single exam score. Okay, well, I'm going to go ahead and stop my share. Um, and I'm going to stop my recording.